Today in class we looked at the derivatives of three inverse functions. Before we do that, we're going to review the derivative of the tangent of x, which is secant squared x, the derivative of sine of x, which is cosine of x, the derivative of e to the x, which is e to the x. Next, let's write the inverses of these three functions. Y equals tangent of x. Remember, for an inverse, we're going to swap the x and the y. And we're going to solve for y. So y is going to equal the arctangent of x. For the y equals sine of x, swap x and y. Solve for y. Y is equal to the arcsine of x. Y equals e to the x. I'm going to swap x and y. How do I solve for an exponent when the base is e? I use natural log. So we're going to say y is equal to the natural log of x. Our goal today is to know or learn where the derivatives of these three inverse functions come from. In the end, I'm not going to make you do that process, the process we're going to go through. We're just going to know the rule. So we're going to try to find out what these three derivatives are. Okay, so we've always looked at derivatives so far where we have a function of x, y in terms of x. Here we're going to look at what's called implicit differentiation. Implicit differentiation allows us to take a derivative of a function with respect to x when the function has y values or y variables in it. So take a look at this function here. This is actually the graph, or the graph would be an ellipse. And I could actually solve for y in this equation and get this positive or negative square root stuff. And I could actually take this derivative. But it is possible for me to take the derivative, find the derivative of y with respect to x, without solving for y. This is important. Sometimes it's inconvenient, difficult, or downright impossible to solve for y. If that is the case, then we have to use implicit differentiation to find the derivative. Let's look at three examples. Number one, I want to differentiate x cubed with respect to x. Remember, this is the same as saying y is equal to x cubed. Find dy dx. That notation just means find the derivative of x cubed with respect to x. Notice these variables agree. X in the function, x, I want to take the derivative with respect to x. Just use the power rule. We've got that down. Number two. 2 says y cubed is our function. Okay, so think about this. Whenever we talk about y, it has been a function of x. If I want to take the derivative of y, then the derivative of y with respect to x is f prime of x. In this example, I want to differentiate with respect to x. My function is in terms of y. When the variables do not agree, we apply the chain rule. So, what's the derivative of y cubed? That's 3y squared. I'm going to think about y being a function of x. So I have to apply the chain rule here and say I'm going to take the derivative of y with respect to x. So there's where the chain rule just happened. Here's our third example. I have two pieces. In the first piece, the x variables agree. I take the derivative just as I normally would using the power rule, and I get 10x to the fourth. The second term, 3y, does not have a variable x, so these variables disagree. I'm going to differentiate 3y with respect to x by using the power rule. I get 3, and here this dy dx is the result of taking the derivative of y with respect to x. the chain rule. Let's take a look at two examples. See if we can get the hang of this. So example number 1. I want you to write down that we're taking the derivative with respect to x of the left-hand side and of the right-hand side. Let's take the derivative of the right-hand side first. That's an easy one, 4x to the third, just using the power rule. Notice the variables agreed, so we just take our derivative as normal. In the second one, the variables do not agree. We're going to need to apply the chain rule. So what's the derivative of negative 3y squared? That would be negative 6y times the derivative of dy dx. I want to solve for dy dx. I'm going to divide by negative 6y and reduce to get negative 2x cubed over 3y. Alright, question number 2. Well, I think I changed this on our notes, so I'm going to change this here. I did, instead of this function, I did y squared minus 7y. Okay, we're going to take the derivative of the left-hand side, y squared minus 7y, and the derivative of the right-hand side, both with respect to x. So I'm differentiating the left-hand side using the power rule. I get 2 times y. Remember, y is a function of x, so I'm going to multiply by the derivative of dy dx. Negative 7y, derivative is negative 7. Y is a function of x, so I must multiply by the dy dx. We just applied the chain rule in both of those situations. Okay, the right-hand side. We do need to use the chain rule here. We first start with the derivative of the cosine of something. That's a negative sign. Of the same something times the derivative of x cubed, which is 3x squared. We just applied the chain rule. Alright, how do we solve for dy dx? Let's factor on the left-hand side. On the right-hand side, I'm going to bring the coefficient of 3 to the front. I'll bring that x squared as well. I'm going to divide by 2y minus 7. So I'll get negative 3x squared sine of x cubed over 2y minus 7. Okay, so we're now going to find the derivative of the arctangent of x. We're going to start by saying y is equal to the arctangent of x, and rewriting this to say x is equal to the tangent of y. Let's implicitly differentiate both sides of this equation with respect to x. We're going to get 1 is equal to the secant squared of y times dy dx using the chain rule. We're going to isolate dy dx by dividing by secant squared y. Another name for secant squared y, 1 over secant squared y, is cosine squared of y. We need our answer to be a dy dx in terms of only x, and here we see it's in terms of y. So let's go back to our definition that x is equal to the tangent of y, and let's draw a picture of the angle whose tangent is x over 1. The hypotenuse in this scenario would be 1 plus x squared under the square root. And now, can you tell me the cosine of y? Using the picture, the cosine of y is 1 over the square root of 1 plus x squared. We are going to square that quantity and get 1 over 1 plus x squared. That is the derivative of the arctangent of x. Okay, let's repeat this process with the arcsine function. Y is equal to the arcsine of x. We're going to rewrite the arcsine function to be x is equal to the sine of y. We're going to differentiate both sides of this equation. 1 is equal to cosine of y times dy dx. We're going to isolate dy dx. And we could call that secant of y. We want our derivative in terms of only x, not y. So let's use this equation and draw a picture representing angle y. Angle y has a sine value of x over 1. So the horizontal piece of this triangle would be the square root of 1 minus x squared. Replacing the secant of y with the actual secant of y in using the triangle. Remember, secant of y is the reciprocal of cosine of y. Cosine of y is the square root of 1 minus x squared over 1. So secant of y is 1 over the square root of 1 minus x squared. All right, last one here. We have the natural log of x. We're going to say y equals the natural log of x. We're going to rewrite this and say x is equal to e to the y. We're going to differentiate both sides of the equation. 1 is equal to e to the y times dy dx. We're going to isolate dy dx. And we need to replace e to the y with an expression of x. And you'll notice that right here, we know that e to the y is x. So let's just replace it. dy dx is 1 over x. So the derivative of the natural log of x is 1 over x. All right, let's see if we can do, first of all, fill in your formulas for the derivatives. 1 over 1 plus x squared for arctan, 1 over the square root of 1 minus x squared for arcsine, and 1 over x for natural log. Let's try a couple sample problems. First problem, we have an outer function and an inner function. So I'm going to note this as f of x is the arctan of x. What is its derivative? 1 over 1 plus x squared. I'm going to note the inner function, g of x, is x squared. G prime of x is 2x. We're going to use the chain rule on this. We need the outer function derivative, so that's 1 over 1 plus something squared. What goes inside there? Oh, my t squared goes inside there. Sorry, I used x's instead of t's. Then I'm going to multiply by the derivative of t squared, which is 2t. In the end, the derivative of this function is 2t over 1 plus t to the fourth. 2t over 1 plus t to the fourth. Okay, let's take a look at the next function, the derivative of arcsine of tangent of theta. Okay, identifying the outer function, f of x is arcsine of x. Its derivative is 1 over the square root of 1 minus x squared. The inner function, I'll call it g of theta, is tangent of theta. Its derivative, g prime of theta, is secant squared theta. We're going to use the chain rule in this scenario. So that means we're going to do 1 over the square root of 1 minus something squared. That inner function is tangent theta. We're going to multiply by secant squared theta. So in the end, this derivative is secant squared theta over the square root of 1 minus tangent squared theta. If this had been a plus, we could do some simplification, but it's not. Let's try our last one. Outer function is the natural log of x. Its derivative is 1 over x. Inner function is x squared plus 1. Its derivative is 2x. Taking the derivative, we have 1 over x squared plus 1 times 2x. And that's pretty well done.